Okay, now we are interested to find the condition for optimum pressure ratio at which the net work done will be maximum. So first of all, we have to write the expression for the net work done. For that purpose, we draw a Brayton cycle on TS diagram. One to two is a compression. In the compression, 2 to 3 is a combustion in the combustion chamber, and 3 to 4 is a expansion in the turbine. So at this line P1 equal to P4 is equal to constant, and at this line P2 equal to P3 is equal to constant pressure lines. So W of compressor is equal to Cp of T2 minus T1, and W of turbine is equal to Cp of T3 minus T4. So we can write W net is equal to W turbine minus W compressor is equal to Cp of T3 minus T4 minus Cp of T2 minus T1. Okay, so let me take T3. T3 is the maximum temperature. T3 is common. T3. Now let T3 is outside the bracket, and we get 1 minus T4 by T3 minus Cp of, from this bracket we can take T1, T2 by T1 minus 1. Remember that T3 is the maximum temperature of the cycle and T1 is the minimum temperature of the cycle. This is T1 and this is T3. T3 is the maximum temperature of the cycle, entire cycle. Okay, so Cp T3 in bracket 1 minus T4 by T3. We know that very well. T3 by T4 is equal to T3 by T4 to the power gamma minus 1 over gamma is also equal to Rp to the power gamma minus 1 over gamma. Rp is the pressure ratio. Okay. Similar pattern, we also know that T2 by T1 is equal to Rp to the power gamma minus 1 over gamma. Okay. So use these relations. In this equation we can write 1 upon Rp to the power gamma minus 1 over gamma minus Cp of T1 Rp to the power gamma minus 1 over gamma minus 1. This is the expression for net work done in terms of pressure ratio, because we are interested to find the condition for optimum pressure ratio. That's why we are writing the equation of W net in terms of pressure ratio. Okay. For the simplicity, we can take gamma minus 1 over gamma as x. For the simplification, in the last stage, we can put the value of x in the expression as actual. Okay, so for now W net can be written as is equal to Cp of T3 in bracket 1 minus Rp to the power minus x and minus Cp of T1 Rp to the power x minus 1. Okay, so this is the expression for net work done. Now we are interested to maximize this work done. So for maximum net work done, then d of W net divided by d of Rp must be equal to 0, because the expression is vary with respect to Rp. Net work done is vary with respect to pressure ratio. So we have to differentiate the equation with respect to Rp. So we get d of W net divided by d of Rp is equal to Cp of T3. 1 is 0 differentiation of 1 is 0 minus plus x rp to the power minus x minus 1 minus cp of t1 is constant rp to the power x times rp to the power x minus 1 minus 0. Okay, so equate this as 0. Now equating this as 0, so from there we get t3 by t1 is equal to t3 by t1 is equal to rp to the power 2x. Okay, now put the value of x as gamma minus 1 over gamma. So we can write rp is equal to, from there we can write rp is equal to t3 by t1 to the power 1 upon 2x is equal to T3 is the maximum temperature of the cycle. T max divided by T1 is the minimum temperature of the cycle. Okay, to the power 1 upon 2x. X is 2 times gamma minus 1 divided by gamma. So I write gamma in the numerator. This is the expression we get for Rp. This is the expression for Rp when the work done is maximum. So this is the pressure ratio, and this pressure ratio is called as optimum pressure ratio. Ratio is Rp optimum. Okay, at this optimum pressure ratio, the net work done in the cycle will be maximum. Okay, now in the diagram we can see the variation of Rp pressure ratio with respect to variation of work ratio or work done, net work done with respect to pressure ratio. So we can draw a diagram where we can see this is the Rp optimum for air. This is the graph for work done when the working substance is working fluid is air. Then this Rp is called as Rp optimum. This is the maximum work done. Okay, if we are draw the graph for helium, then we get the curve like this, and this is the Rp optimum for helium. This is another gas, the working substance. This is the maximum work output, maximum net work done. Okay, so we analyze one thing here, that the maximum work done is achieved in case of helium at the lower Rp optimum compared to the air. So it is because of higher or major properties of the thermodynamics or more desirable properties of the thermodynamics, because helium having the more high specific heats, helium having high specific heat, Cp is greater, higher Cp compared to the air. Air ka Cp is lower. That's why this helium is more efficient and gives you the higher efficiency when you are using the helium as a working substance. That's why there is a reason in the closed gas cycles helium is used as a working substance, and in case of open gas turbines air is used as a working substance. Okay, if you are interested to draw the curve for efficiency, then the curve is like this. This is the curve for efficiency, thermal efficiency of the gas turbines when air is used as a working substance. This curve is for air. And if you are draw the curve for helium, then you will get the efficiency, thermal efficiency of the Brayton cycle when you are using helium as a working substance. Then you can also observe that the efficiency is increased, thermal efficiency of the Brayton cycle or gas turbine cycles increases as you are using more efficient working substance like helium argon gases. Okay.